Hello and welcome to our live coverage of the American Astronomical Society's 233rd meeting. And coming to us live, well, I am Dr. Pamela Gay and I'm in Southern Illinois. But with me, which is super exciting, is... Oh, you are much better than a poor substitution. And oh my gosh, that skyline, absolutely amazing. So tell us how the conference has gone so far. Excellent. So uh, to back up for our audience, you arrived there Saturday, you set up, Sunday was the first real day of the conference, and the information at this conference is presented basically in three different ways. There's the big invited talks where you have hundreds, thousands of people crammed into one room, and the talks go from 20 minutes to a full hour. You then have micro talks, which, depending on if they're a regular presentation or a PhD presentation, are like max 12 minutes. And then we have poster presentations where we create posters and folks like you stand in front of them to discuss your results. Now, what all have you seen? I heard that there was like plenary session awesomeness.
So
Okay,
yeah,
so
lots of
so
orbits, really great
unsurprising
image.
to everyone, I goofed your audio.
All right. At what part did my audio get
Like
you?
ever, like ever.
Like effort. All right.
So
Plenary.
start with last night's plenary, and I'm in the process of trying to find. She actually went through. You describe it, and I'm going to keep trying to find the information to share.
All right. So last night's plenary, which I unfortunately missed because it was not announced, and it happened to be when we were going out to dinner. Um, she took the bottom 10% of her slides and added essentially experiences of what she'd actually seen, had done to her, experience, et cetera, et cetera, et cetera, et cetera, as a woman in the Astronomy field. Yes. Words. Words are hard.
They are.
This was not announced beforehand, and I saw it on Twitter and immediately regretted skipping. So that was last night's plenary. There are pictures out there on Twitter. Look under the hashtag AAS233 and you'll find some of them. So this morning's plenary, which I did go to, they took lots and lots and lots and lots and lots of shots of essentially half of Andromeda, and I'm thinking it's over 1,000 orbits. And I think it's the PHAT program, PHAT. But essentially, at some point, there was a call for some crazy proposals, things that you've never asked for. They asked for 1,000 orbits, they got 1,000 orbits. And it was amazing. And she started it off with, each one of the green squares that you see when you're, browsing the archives for images, and they just kept adding up. It's amazing. And I guess this whole thing took years and years and years, and she just kept adding people to help her, deal with all of this. And there were also a couple neat animations about star ages, and I don't remember all the details because pretty pictures, amazing, time-consuming pretty pictures, and they got a whole lot of data from that. 1,000 orbits is crazy.
Each orbit is 90 minutes. So you're looking at 90,000 minutes of Hubble time. I've got no words for that.
Yeah.
Now, I did find the reference to last night's speaker. It was Caitlin Casey. And she posted an entire Twitter thread where she went through each of the things that she had at the bottoms of her slides that were the distractors that made it so much harder than it would have been for a white male to accomplish research. And the reason this was unannounced, the reason that no one knew this was coming, is she wanted people to not come with a chip on their shoulder and prepared to heckle and all the other things that people do. She wanted people to be there for the science and then to get that secondary message as well. It was a pretty powerful way of doing things. Now, for those of you who want to follow along with everything that's going, there are links to this meeting off of AAS.org. This is meetings/AAS233. And not everything is publicly accessible, but we're doing what we can to take what is publicly accessible and bring it all to you here. Now, you've also been going around the meeting, and I'm going to bring up some of your photos. And as you've been going around the meeting, you have caught bits and pieces of a whole bunch of different stuff and things. And I have to admit, you are very good at taking photos of things that color coordinate to the backdrop. So we have fact, galaxies are cool and galaxies are fiendishly complicated.
Yeah, that was from this morning's plenary. That she had 2 slides exactly in that order for the talk. I was very, very impressed. She has mad PowerPoint skills and all the props to her. And yeah, there's a bit of humor in there and lighthearted, and definitely not a dull early morning talk. It was enjoyable.
And that is what we all need. Now, you also hit on the Astronomy on Tap presentation while you were there. And this is a nationwide program where we actually have Astronomy on Tap here in St. Louis. For those who don't know about it, can you say a few words?
So they are kind of diagonally across from my informed consent poster. So I just stared at their poster and was able to snag a shot. But essentially, it sounds like they have a bunch of speakers so the audience doesn't get overwhelmed, and sounds like they meet at pubs and things. And all of these things are happening in a whole bunch of different forms all over the world, well, the Western world, because their map looked mostly like the US and Europe. But it's pretty amazing.
Yeah, it's very much a Western program. And this is because of the prohibitions against alcohol and the lack of pub culture in many places on the planet. You really do need that pub culture. So we have 2 more minutes left. I'm noticing there are a whole lot of JWST in Lego, in model, in all sorts of other forms. So in our final couple of minutes, can you tell us about the JWST presence at AAS?
Yeah, there's JWST people here, mostly contractors, and Bell Aerospace also has a JWST model out. That's not the one that I have a photo of. The photo of the one I have was me trying to catch a selfie, the one at the NASA table. And the Lego is not JWST. I forget what it is. One of the photos I took totally has the name of it in. There are no plans for it. I asked the builder, he's like, no, there's no plans, but there will be a JWST Lego model coming out this summer on Lego Ideas, so we can all vote for that. So I'm excited about that. But this Lego model is pretty freaking cool.
It
really is. It folds up and everything.
So next Hangout-a-thon, we pit you and Fenmill against each other to build the JWST?
Sure.
You might get it done before the real one's done.
Yeah. Yeah. I am ashamed to admit that, yeah, I think that's really what's going to happen. We'll all have these beautiful Lego JWST models at home, and they'll still be building the JWST.
So what's next on your agenda?
Go back to the exhibition hall and check out more of the exhibitors and vendors, and there's a bunch more cool stuff in there that I haven't had a chance to see yet, and then go and hang out by my poster for the 5 o'clock session.
That all sounds fabulous.
Yep.
And we're going to have you back tomorrow, same bat time, same bat channel.
Totally.
Okay, so I'm going to let you go. We're going to switch over to the press conference. Thank you so much, Annie. Mm-hmm. Remember to eat, drink, stay hydrated, because we know sleep isn't going to happen.
All right, bye.
Bye-bye. So I'm now going to transition things. Wow, we have chaos occurring. I'm going to transition things over for the beginning of the press conference. Please bear with me for a moment while I rearrange our screens. So for those of you who don't know what you have stumbled in upon, my name is Dr. Pamela Gay, and this is CosmoQuest. We are here to put science in your brains. Today, we are bringing you live coverage of the American Astronomical Society meeting out in Seattle, Washington. There are roughly 3,000 astronomers from around the world, all gathered to present their science, discuss new ideas, and figure out how to collaborate on discovering our universe into tomorrow. Things are a bit crazy this year because of the U.S. government shutdown. NASA scientists, National Science Foundation representatives, anyone who works for the government is not allowed to be in attendance. They aren't even allowed, according to the Office of Management and Budgets, to volunteer their efforts. So a lot of key people just aren't able to be there. But we're going to do what we can to bring you what we can and keep the science going. Now, things should be starting any moment. Let me transition over and see what I can do to get us the presentation.
topic and the panelists. They're going to speak in order. We'll hold all the questions to the end so that we don't step on anybody's time allotment. All right, so I don't know how many times we've done it, but we've had a lot of press conferences from the Sloan Digital Sky Survey because it's kind of the Energizer bunny of sky surveys. It's been around a long time, and it just keeps going and going. Today we're going to hear a number of reports from some of the latest incarnations of Sloan, which is actually many different kinds of surveys in one. So we're going to start by hearing from the project's scientific spokesperson, Karen Masters, who's now at Haverford College. She's going to talk about how does SDSS keep going and going, past, present, and future plans. Then David Nidever from Montana State University is going to talk about it is never too late to be active. Apogee chemical abundances of the Large Magellanic Cloud reveal a lazy past and an active present. Then he'll be followed by Renbin Yan from University of Kentucky, Science in the Library, a new library of stellar spectra. And finally, Rebecca Nevin from the University of Colorado. How do you pronounce that acronym? Is it MANGA? Okay. Mining MANGA for mergers, accurate identification of galaxy mergers with imaging and kinematics. All right, and with that, I'll turn it over to Karen, and we'll get started.
Hi everyone, I'm Karen Masters at Haverford College near Philadelphia, and I'm the scientific spokesperson for the fourth phase of the SDSS. Rick mentioned to me that he had deja vu. I think I do too. I knew he was going to say we were the Energizer bunny of science, and so I made my slide accordingly. And I hope to give you a little bit of an update of the past, present, and future of SDSS and how it is we keep going as a survey. So believe it or not, we have 19 years of Sloan Digital Sky Survey data, more than 20 years since we've been on Sky. That has totaled 15 public data releases. So our funding and our sort of collaboration, our ethos is very much open science, open data, and has been from the very beginning. Our most recent data release was data release 15, which just went live last month. We have imaging over 35% of the sky and millions, literally millions of spectra. 4 million, I think, is out of date, and thousands of scientific papers and hundreds of thousands of citations. So Sloan is creating a bit of a buzz at this meeting for our plates, our plug plates. There's one of them just down by the podium here. These are drilled uniquely for each patch of the sky, and so we go through quite a lot of these. We plug optical fibers into them. But just want to kind of emphasize that we're not done as a survey. We keep going. And in particular, the fourth phase that I'm the spokesperson for, we have three main aspects. The fourth phase will run through 2020. So Apogee is measuring spectra of stars in our own galaxy, and infrared spectra in particular. EBOS is our sort of classic Sloan survey. It's our mapping distances to galaxies, going deeper than ever before. And MANGA is a new kind of venture for Sloan. So instead of a single fiber on each object, we bundle the fibers, and so we can make those spectral maps of galaxies in MANGA. And this survey is going incredibly well. So I wanted to give you some superlatives. So MANGA is the largest.
So sorry, I'm trying to figure out how to get the window back and get the chat back for the conference, and the issue that I'm running into is it's not letting me get the chat for the press, and in the process of trying to grab it out of my history, I broke the universe. Let's see if I can get this back.
Means we can get the kinematics of every star in that galaxy. So that's the kinematic map where blue is moving towards us and red away from us with respect to the center of the galaxy. But we don't just get it for stars because this is spectra. We can do it separately for gas, and actually you can do it separately for different ages of stars, which is really cool. We also get metallicity. We can measure how many heavy elements there are at each point of the galaxy. So that's a map of that for that galaxy. Other things, so this is kind of a technical thing, D4000, it's a feature in the spectra which correlates with the age of stars. So this is kind of like mapping the ages of the stars in this galaxy. And, you know, the H-alpha flux tells you where the stars are forming. So you get a map of current star formation. We get so many of these different maps. I've just given you some of my favorite highlights, my favorite maps from manga. This enormous amount of science is coming out of this survey, which is now the largest of its kind in the world. Apogee's superlative is that it's the only survey doing what it does in both hemispheres. So it's the only survey mapping the galaxy, taking spectra of the galaxy from both hemispheres. We have the same instrument on the Sloan Foundation telescope and the DuPont telescope, which is in Las Campanas in Chile. And you'll hear a result today, which is, you know, not possible unless we had a southern instrument. I don't want to leave EBOS out. EBOS has been busily observing, and in fact will finish observing next month, which means they're going to do all the final cosmology analysis papers in the next year. So stay tuned for cosmology, really nice, exciting cosmology results a year from now. The EBOS is kind of filling in this gap where between some of the future surveys that are coming and the previous Sloan maps. So here's a cosmology result which Sloan contributed to in the past, the contents of the universe. This is the pie chart. You know, 70% of the energy is dark energy, 24% dark matter, 5% atoms. With thanks to our project director who gave me this slide, we can turn this into the Sloan funding pie. How does Sloan actually do what it does? We do it with extremely little government funding. So the Department of Energy just funded about 4-5% of the Sloan 4 program. The Sloan Foundation gives us instrumental seed funding to get us going. That totaled about 25% this time. And our member institutes give us 70%. And we don't know if that same funding model will go on to Sloan 5, but Sloan 5 has got the Sloan funding now and is actively soliciting members to join. And instead of using human fiber optic plugs, Sloan 5 is going to move to robotic plugging and therefore be able to do many, many, many more objects, and again, in both hemispheres. So we need a new logo. That's the new logo. And Sloan 5 will be coming soon, and much more exciting science from Sloan for many years to come, I think.
Okay, so today I'd like to present some exciting results from the Sloan Digital Sky Survey on our two nearest neighbor galaxies, the Large and Small Magellanic Clouds, which you can see here over the Las Campanas Observatory in Chile. So one of the large outstanding questions in astronomy is how galaxies form and evolve over time. Well, we're getting a better picture of how large galaxies like our Milky Way formed. There are many more small dwarf galaxies that you can see here in this picture from a computer simulation. Dwarf galaxies are by far the most common galaxies in the universe, and we'd like to understand them better. This has been challenging because dwarf galaxies are intrinsically faint and most are very far away. But luckily we have two dwarf galaxies right next door that we can study in great detail. These are the Magellanic Clouds that you can see here and can only be observed from the southern hemisphere. The Magellanic Clouds are the largest satellite dwarf galaxies of our own Milky Way and are currently tumbling into the Milky Way. They're very nearby. In fact, they're so close that they extend over a very huge part of the sky, and it's been challenging to map out their full structure. Most past studies have really focused only on the central parts. But now that's all changing. So almost 2 years ago, the Sloan Digital Sky Survey got a new eye in the southern sky. This is the southern apogee spectrograph, with which we can observe 300 stars at a time in the near-infrared wavelengths over a large patch of the sky. And with this new capability, we can explore the Magellanic Clouds like never before. So how does this all work? The spectrograph breaks up the light from a star into its individual wavelengths, and we can detect the absorption lines from atoms in the atmosphere of the star. Here's an example of two stars that are very much alike, except that the one on the top has very few heavy elements, and the one on the bottom has lots of heavy elements, and therefore lots of absorption lines. So we are obtaining precise spectroscopic observations of 5,000 stars in the Magellanic Cloud. clouds, which allow us for the very first time to create chemical abundance maps of these dwarf galaxies. This is showing our map of the heavy elements of the stars in the Large Magellanic Cloud over a background optical image. And the shapes here are due to the Sloan plates, which we are using to make the observations. So stars and galaxies have different chemical compositions due to the chemical evolution that is produced by this cycle I'm illustrating here. The first stars form from dense gas clouds, and at the end of their lives, these stars explode in supernovae and pollute the surrounding gas with heavy elements. The next generation of stars then forms from that gas and has a higher concentration of those heavy elements. And this cycle continues continually in a galaxy, enriching the gas and stars with heavy elements until basically you run out of gas. And the speed at which this happens is regulated by the star formation rate in a galaxy. For the elements that we are looking at, there are two main types of supernovae that create them. So they're the high mass star supernovae. They create these alpha elements, magnesium, calcium, silicon, and others, as well as iron. The other type is the low-mass star supernovae, which create mainly iron. The other difference is that the high-mass star supernovae, they go off almost immediately once you start forming stars, and the low-mass star supernovae go off. There's a delay of about a gig-year until they start exploding. So how do we actually use the data to understand the evolution of the Magellanic Clouds? So in this plot, on the x-axis, I'm showing the total amount of heavy elements in a star formed from both types of supernovae. On the y-axis, I'm showing the ratio of those alpha elements only formed from the high-mass star supernovae over all elements. Now, at the beginning, when a galaxy starts forming stars, you just have contributions from those high-mass star supernovae. And then once that 1 gig-year has passed and the low-mass star supernovae go off, you get them forming no alpha abundances, no alpha elements, and you get a downturn. So to show how this works, I'm showing a model of the Milky Way which we got from the apogee data. So here we are continuously forming stars, and it's going down once those low-mass supernovae turn on. And what happens is that the Milky Way has a very high star formation rate, so it was able to form lots of heavy elements before the low-mass supernova turned on. So in contrast, if we then add the Large Magellanic Cloud to this, again, a model from our observations, this is what the LMC looks like. You can see that it formed very few heavy elements before the low-mass star supernova turned on. And this is due to a very low star formation rate. So initially, for the first 10 gigayears, it had a very low star formation rate, 50 times lower than the Milky Way. However, it's never too late to get active. So if we look actually at the full 13 gigayears here, you can see that very recently they had an increase in the number of alpha elements due to an increase in star formation rate of about a factor of 6. This starburst was triggered by a close encounter of the Magellanic Clouds with each other. So here's the actual data, the apogee data in which we based these model, and you can see the lazy past and then the active future, active current. So just to summarize, we've been using the Southern Apogee Spectrograph to perform the largest spectroscopic survey of the Magellanic Clouds to date and creating chemical maps. We have found that the Magellanic Clouds had a very lazy past with a star formation rate 50 times lower than the Milky Way. In the last couple of gigayears, they had a rapid increase in their star formation rate of 6 times due to their close interaction with each other. Thank you.
Okay. So here we are announcing the first release of the MANGA Stellar Library. MANGA Stellar Library is a library of spectral stars. What does that mean? It means we are providing high-quality spectra like you see here at the bottom of the screen. for thousands of different types of stars. And this is an essential tool that is needed by a large number of astronomers, and in particular, people who study galaxy evolution. So why do stars have anything to do with galaxies? Because galaxies are made of stars. If you look at any random distant galaxy you see on the screen from the Sloan Digital Sky Survey Sky Server, you see a smudge of light. And any tiny region in that smudge of light is made by, light there is made by millions to billions of stars. As you do in MANGA survey, for that region, you get the combined light from all the stars. But we astronomers want to figure out what mix of stars make up that light, so that we can understand the star formation history of the galaxy, so that we can weigh the mass of the galaxy. Figure out what mix of stars are making up the light from the combined spectra. It's a bit like hearing a symphony. When you go to a concert and hear a symphony, you hear the sound of all the instruments at once, all the musical instruments at once. Each instrument playing by itself, then you would have no idea what instruments are playing. So in order to know what instruments are playing, you want to play each instrument by itself, study its tone, so that when you hear instruments are there. This is exactly what we do in studying galaxy evolution. Now imagine a galaxy made of only 2 stars, simplified model. If you have a star 1 that have a spectrum look like this, you can see a curve on there from blue to red, and this is showing you the intensity of light at different wavelengths. You can see wiggles in there, that's the spectral features. And this is another star that you can see has very different shapes and different wiggles in the curve. If you combine the light from the 2 stars, you get the combined galaxy light, as you see there. In most cases, for distant galaxies, we don't see individual stars. We see the combined light. So we want to figure out what mix of stars make up that light. So in order to do that, we need to get the spectra for each type of star by itself. And this is what the library is. So we are making a large library including thousands of different types, and just showing you some examples here from very hot stars to cooler stars. And you can see they all have different shapes, you have different wiggles in the spectra. And these here are cooler stars, and here are some giant stars. From these wiggles in the spectra, you can tell the surface temperature of the star, you can tell the size of the star, you can tell the chemical composition of the star. So because stars vary in many different chemical composition, we need to sample a large number of each individual types. So this is captured in this plot, the Hertzsprung-Russell diagram of the MANGA star library. Each point here represents 1 star in the library. I'm showing you the vertical axis is the luminosity or brightness of the star from faint to bright, and
You mentioned something that made me go, and that was the LNC self-management rate increase is due to a new molecular class or FMC design. So how would you compare that to the capacity of training monkey way that triggered that? How
Yeah, so the Magellanic Clouds have kind of been orbiting around each other for the last 4 gigayears, and they had a very close encounter not that long ago, and that triggered these starbursts in both galaxies, and that's why they have this rapid increase in their star formation rate. And they'll be plummeting. They're plummeting into the Milky Way now. So the next couple gigayears, they'll be absorbed into the Milky Way. Yeah.
Space.com. So I was going to ask you what the time frame was on that, and then another question. So when I saw
For which part?
the recent uptick, sorry.
About 2 gigayears ago is when that happened. So the increase of the star formation rate was by a factor of 6, roughly.
And then the other question I had was, how come the Magellanic Cloud started off so much slower than the star formation in the Milky Way?
So that's mostly just because they have a very low mass. So you have more gas, you form more stars. But actually, one of the surprising things about the Magellanic Clouds is that their star formation rate is even lower than you'd expect for their mass. So even other galaxies like Fornax or Sagittarius, which are lower mass than the Magellanic Clouds, the Magellanic Clouds have a much lower star formation rate. And that's kind of a mystery. We think that might be due to the fact that the Magellanic Clouds formed far away from the Milky Way originally in a low-density environment, and then only recently fell into the Milky Way.
Okay. Other questions? We have any more? All right, that's my opportunity. So my question is also for David Nidever. So you showed, a history of star formation in the Magellanic Cloud. I wonder if you can just elaborate a little bit on how you're getting ages. How do you know that you're looking at a time sequence there? Because you're looking at all the stars now.
Right. So we don't actually have ages yet for the individual stars. What we do have is their chemical makeup. And so we came up with a chemical evolution model to try to fit that chemical makeup of the different stars. And so we can basically fiddle around with different parameters in the model, for example, the star formation rate and how that changed over time. And we basically fit that to match the data. And that's what allows us to pull out the star formation rate as a function of time. And that's what I was showing with those movies.
Right. Yeah. Okay. I have a question for Raymond as well. This library is separate. Obviously, we'll have multiple uses. I'm wondering if we can other than just trying to disentangle the mix of stars that are in a galaxy, can you think about some other potential uses for this library? What other kinds of scientific investigations can you make with such a high-quality set of stellar spectra?
Yeah, it can be used in many different fields, from stellar astronomy to cosmology. In cosmology, you quite often need to fit the spectral energy distribution of distant galaxies in order to figure out how far they are. When you don't have a spectrum, sometimes you have multiple photometry bands. You can try to use the right stuff in different bands. How far something is. That you would need stellar population models to do that modeling. That relies on the stellar reactivity stellar as well. And we use it to measure the mass of stars. So the stellar mass of distant galaxies. Stellar mass of distant galaxies in galaxies on the stellar astronomy, we use it to measure parameters of different stars. For example, if you take any random spectrum of any random stars, you want to figure out what are the temperature, surface gravity, and the kind of composition of the star. You can use the stellar library to fit the spectra and to get the parameters. Even for people who study exoplanets, they need to subtract the stellar light in order to detect the light from the exoplanets, or to use that to measure the exact parameters for the stars. So they also need to use the stellar library as well. So it's really essential to use by a really wide range of astronomers.
Mm-hmm. And a question for Rebecca. You showed a picture of a spiral galaxy with a couple of spots near it, and you said that it was a minor merger. But how do you, in that particular instance, how do you confirm that that's a merger rather than a large galaxy with a couple of small satellites like, M31 with its 2 small satellites? Or are you saying that in any situation where you have a big galaxy with 2 little galaxies around it, if you wait long enough, they'll merge?
That's a good question. So what I showed with those orange-looking images, so that I know for sure because those are the simulated galaxies, right? So that's the trick, is that you use the simulation so that you know going in if something is emerging or not actively. I would say to that question, though, something that's been really interesting about applying this technique to real Sloan galaxies is that I have a tool that goes out and identifies minor mergers like the one I showed. And I have had to be the follow-up checker of, are those really minor mergers? But I haven't really developed a technique that I'm fully happy with yet. So this will be a next paper of how to confirm if it's actually finding a minor merger, or sometimes you can find something that's actually just a clump of star formation in the galaxy that might look like a secondary tiny galaxy.
So will you take spectra, basically?
Right. There's going to be multiple follow-up methods I need to develop to actually check the method for real in the Sloan galaxies. Yeah.
Okay.
It's going to be hard.
All right. We have a question over here. Please remember to identify yourself.
I am Jonathan Davis from Utah Valley University. For question for Rebecca. So you might have, might just be a follow-up on what you were just saying, but when you showed that iMovie with the 2 galaxies merging, it was a great movie, by the way. It was, at the very end, you had 2 spiral galaxies that ended up as an elliptical. Does your software have any plans in the future that you might be able to identify, how these galaxies are going to end up after they have merged? Or they'll be able to identify, an elliptical that has merged or something?
Oh, I think that's a really good question. So your question is, are you able to distinguish between when it is in the merger or if it just merged? Sorry, I'm just trying to clarify.
So my question is, how do you distinguish how the galaxy is going to end up after the merger?
Right.
And does your software able to distinguish between a galaxy that has gone through a merger and whether it's going to become a spiral to an elliptical after it's finished?
Right, so you just touched on something that is actively happening in galaxy evolution, is what happens when galaxies merge. So these simulations are disk galaxy mergers, and they do form more of an elliptical looking galaxy afterwards. And I think I would just say that the technique is really strong because it identifies galaxies that are about to merge as well as galaxies that have merged. So it really incorporates multiple different things about the images. So one thing that I didn't mention that it looks at is the concentration of light. So that actually goes up for galaxies after a merger. So that's one thing that it's sensitive to, is how concentrated is the light. So it's able to find galaxies that have already merged and maybe are just done merging, and it's been only 1 billion years after the merger.
Thanks.
Okay.
Anything online? Anybody else have a question? All right, I'll have one for Karen. So you stressed that this program's been around for around 2 decades now. It's the same telescope. I remember seeing a picture when that telescope debuted as, it's 2.5 meters, right? So I'm assuming that part of why this survey continues and why you keep, you invent new projects that it can do is because of instrumentation evolving, right? Which is very similar to what's happened with Hubble. It's the same telescope, but it's got all these new instruments. So can you give us just a sort of high-level idea of sort of what kind of gains you've had in terms of sensitivity over the 20 years, or in terms of your efficiency, things like that? Just how has the technology changed the way the survey is done after all this time? the D in SDSS stands for digital, and as I recall, Sloan was the first digital sky survey. Right? That was what made it so special at the time. So, but CCDs have come, a very far way in 20 years. So presumably you're using much bigger CCDs and much more sensitive CCDs and all.
Can I help answer the question? So over the past 20 years, we have expanded in wavelength coverage. The spectrum has gone to rather in Sloan we go up to in Sloan 1 we go up to 90 to 100 angstrom. Now the dot spectrum goes beyond 1 micron, and we added the infrared spectrum, the FP spectrum. So that's a new thing. And also the number of fibers has increased significantly. Is higher, and the spectra are becoming more efficient in Sloan 3 than previous. And in Sloan 4, we bundle the fibers together to make manga possible, so that all these improvements are making the nuclear database possible.
Yeah. Great.
Yeah.
Okay.
I was just going to add that.
Sorry, go ahead. Go ahead.
I'm right here.
Oh, sorry.
Hi. So to add what Karen and.
Oh, okay.
Yeah. No, it's okay. I was just going to add actually that our detectors, the ones that we use for the apogee instruments, so this allows us to push into the near infrared, which is really important because if you're looking into the galactic center, you have to penetrate through the dust. But those detectors actually happen to be cast-offs from the James Webb Space Telescope. So we have, had an evolution with regard to technology. Plus, just even going and venturing into the near-infrared domain, we've made some really nice advancements as far as making sure that our fibers remain, cool and efficient. And then, of course, like Renbin mentioned and like Karen mentioned, there's the IFU spectroscopy as well. So yeah, we've gone through a couple of epochs of technological advancement.
Okay.
So I just want to add.
And you are?
Juno Kohlmeyer. I'm the director of SDSS5, the next generation, and I just want to emphasize the power of the public data and the power of the collaboration.
Great, thanks. Okay. Last call for questions. All right, well, there's no harm in ending a little early. Gives me time to make a few announcements to the press corps. Again, tonight we have at 5:30 in this room, we'll have a press reception with the Chandra team.
Hello and welcome everyone. To those of you who do not know what you have stumbled upon, my name is Dr. Pamela Gay and I am your host. This is CosmoQuest. We are a production of the Planetary Science Institute working in collaboration with Youngstown State University, and we are here to put science in your brains. We are working really hard this week to bring you live coverage of the American Astronomical Society meeting in Seattle, Washington. While I am at home in Southern Illinois covering all of the broadcast press conferences and answering your questions, our own Annie Wilson is on location. She is currently out on the floor of the conference looking for cool news stories to report on when she comes on stream tomorrow at 5 p.m. Eastern. That is 2 p.m. Pacific and 10 p.m. UT. Now, I am here to answer all your questions, and I am so glad to see so many Raiders here. And I apologize for my failure to remember to unmute myself. As any of you who visit the stream often will encounter, I have issues with the mute button. I like it maybe a little bit too much. So go ahead at me in the questions and I'll do everything I can to answer all that you may have to ask. I'm currently in the process of just closing down the stream in the background. I had a request earlier on to explain a really awesome looking diagram that got presented. Let me just find my screen capture and then I will do what I can to explain this diagram. So Hydropnic is asking, thank you for the bits, is asking, is there a particular topic that they're covering? Every one of these press conferences is themed. The one that we just watched is based around the Sloan Digital Sky Survey and the new science and new plans for this particular telescope that is located at Apache Point in New Mexico. Thank you so much for the bits. One of the things that came out of this is we are starting to get a better and better understanding of star formation in our own galaxy and in nearby galaxies, and how it is that there's this interplay between when stars formed, what their composition was, and how big those stars are. What we're finding is stars that are less metal rich, they tend to evolve hotter, they tend to be more scattered in their luminosity in general, whereas stars that have significantly more metals, they have a very different, one moment, I'm sorry, my husband can't find the dog because she's in here with me. And when you have a tiny puppy, wondering where the dog is often a question. Okay, so to go back to explaining this diagram in detail, this purple line up here, well, let me start from the very beginning. This is what we call a Hertzsprung-Russell diagram or a color magnitude diagram. On the left is exactly how much light is coming off of a star, corrected for that star's distance. So two stars that may be very different distances away from us could be giving off the exact same amount of light. And they've corrected for the fact that those two identical stars would appear different because of their different distances. They've corrected for that, and they've made a plot of these luminosities as a function of temperature. The biggest stars out there that are burning hydrogen and helium in their cores are over here in this quadrant. And as we move through this line called the main sequence, we continue to see stars that are in that first energy generating stage, that hydrogen burning stage in their core. Now here, where the stars, we call this turn off the main sequence, you can see that different stars with different compositions split off at a different point. This is a super cool realization. Now, to repeat what was said during the press conference, the stars that are purple have less heavy elements, less metals than we find in the sun. The stars that are red have significantly more metal, more heavy elements than we see in the sun. The size of the dot tells us how strong is the pull of gravity on the surface of the star. So where we have the largest spots, these are the most massive objects. Where we see the smallest, those are the least gravitationally pulling down upon the surface objects. This is just a cool data visualization I've never seen before, and I was asked during the presentation to explain it because the audio was so bad. And I hope maybe you can all get kind of as excited as I am. So yes, that is a form of the Hertzsprung-Russell diagram. And yes, I do have a Stella with me as we stream. Hannes Vorwerp is asking, so stars with less metal they don't get larger, they actually form larger. It is possible for things that don't have as much metal in them to get more and more mass built onto the star before it ignites and starts, doing its star thing. Systems that have more heavy elements, they are able to, turn off that mass accretion and start burning as stars at a lower mass. This is one of those really cool things that we've been learning in greater and greater detail over time. So Kangrajadi Pueblo, I'm sorry, that's a lot of words. I'm going to go with Pueblo, is saying, can you tell us something about the 2 missions planned by ESA and NASA in 2020 to Mars? What are the differences? So in general, spacecraft are dead to me until after they have launched. The reason for this is they don't always launch, and my brain can only hold so many things at once. I also had a spacecraft I desperately needed for my research not work, and I counted my spacecraft before they launched, and it really hurt my personal research. So that's probably a little TMI. But the bottom line is I can tell you that the US Mars 2020 is a rover that is going to collect rocks in an area of Mars that is constantly revealing new surface. This constant erosion means that the material at the surface hasn't been exposed to the harsh UV light of the sun for a long period of time. And if it has complex molecules, complex carbon-based organic molecules, the Mars 2020 rover is going to be able to collect them and keep them safe in its storage bin. And someday we hope to send another mission to gather up those collected rocks and bring them back to Earth. Now, I don't know a lot about the European mission. I do know that part of its origins were Europe's concerns that because NASA keeps changing how it funds spacecraft, that it would once again run into problems where it co-planned a mission, built its share of the parts, and then at the last moment, NASA wasn't able to do what it had planned to do. So it's a politically complicated launch system for Mars 2020. I'm sorry that I don't know more, but hopefully that's enough to get you started. So let's see what else is here. JWST, by the way. Yeah, JWST is a personal sore point. CosmoQuest was funded by NASA up until December 31st at midnight. But we'd found out back in August that due to James Webb Space Telescope cost overruns, as well as some policy changes, we might lose our funding. And we lost all of our funding. And we're able to keep going because of donations from people like you who've come to this channel and supported us. Your bits, your subscriptions, your donations through Streamlabs, all these things are filling in the gaps left by NASA because, well, they had to find the funding to fund the rest of JWST from somewhere. And my salary was one of the somewheres they found that money, as well as the salaries of everyone working for me. So Thank you for your donations. You guys really do make the science go. So M. Coupon is saying, so my sister asked me if the sun was a star. Yes, it is. Now I want to find a primer for us to watch. I was pointed to Phil Play's Crash Course. Any other good options? Crash Course is really good. Cool Universe. The Spitzer Space Telescope did a really good VOD series back in the early days of podcasting. They kept it going for many years. There's also Irreverent Science. These are all very good programs that I recommend. In addition, of course, my co-host Fraser Kane for Astronomy Cast. Thank you so much for the follow. My co-host Fraser Kane, he has his if you go to Universe Today, you can see the link. It's his Guide to Space YouTube series. Is another good place to go. Let's see what else you are asking. Cosmos is kind of out of date, Paranor, and the modern Cosmos, I have some issues. I wouldn't recommend it as a starting point. So Diablo BG is saying, my favorite objects are pulsars. If you can talk a bit about them, it would be awesome. So pulsars are what happens when stars that are about 1.5 times larger, and this is approximate, I think it's 1.44 is the cutoff, but I'm bad at remembering specific numbers. Skylius is much better at remembering specific numbers than I am. And we need a shout out to Skylius if that hasn't happened yet, mods, please. So pulsars are when you have a massive star that at the end of its life, it just stops generating enough light. And it turns out stars are supported by light. Down deep in the core of stars, nuclear reactions are taking place, layer upon layer upon layer of nuclear reactions for these massive stars. But at a certain point, the core stops having any fuel for these nuclear reactions to use. And without fuel, when it gets that iron core, the light stops being generated. And that balance between the light pushing out and gravity trying to crunch in, that balance stops to be balanced. Or in the words of Dr. Horrible, the status quo is not quo. At this moment, the entire star collapses in. Massive amounts of nuclear reactions take place with this crushing down. Thank you for the follow, Nightwalker. And there's a flash of light. All of this is called a supernova. And what's left behind at the end of the supernova is an extraordinarily dense object made primarily of neutrons with a thin skin of other stuff on the surface. And all the angular momentum from that previously massive star has been crushed down. And like an ice skater who takes her arms and pulls them inwards and starts spinning faster, well, here we're taking a star that might be as big as the inner part of our solar system and crunching it down to the diameter of Manhattan Island. And when that crunching occurs, the object starts rotating extraordinarily fast, sometimes as fast as 1,000 times per second. And due to the nature of luck, sometimes the rotation axis and the magnetic axis of the object aren't lined up. And the result is, as this rotates, and I need to get a piece of styrofoam I can stab, as this object rotates, the magnetic field beams light off each time it goes past towards an observer like us. And so when we look out across the sky in radio light, sometimes in optical light, we can detect these flashes of light. This is really something that you do for the fast ones in radio where you can get much faster data. Now, they're cool, they're awesome, and they're not made of normal stuff. We're not going to become one, our sun is not going to become one, but they're fun to study at a distance. So do we have any other questions out there? They're filled with pasta. They are not filled with pasta. They're filled with neutrons. Is the rotation of the pulsar variable or always the same? At any given day, hour, week, pulsars are more constant than the ticking of an atomic clock. They do occasionally glitch. A change in their magnetic field can cause a hiccup, and we do see them slow down over the fullness of time. This means that when we look at a freshly formed pulsar, it will be rotating much faster in general than a senior citizen of a pulsar. But moment to moment, they are constant. I did not know nuclear pasta, Skylia, so I'm going to need to find out about that one. Not all neutron stars are pulsars. You can have a boring, bland, not rotating fast enough to be pulsary, boring neutron star. So the neutron stars slow down due to interactions with other objects and loss of matter and ingestion of matter. All of these different things have long-term effects, but mostly it's the interactions of its magnetic field with surrounding space. Thank you, Paranor, for the link. So there are pulsars out there that aren't pointed at Earth, but there are also objects out there that aren't pulsars. So you can have it going both ways. All it takes to not be a pulsar is to have a weak magnetic field. You have to have that extraordinarily strong magnetic field if you want to have the pulsar-like characteristics. So the very first planets ever found, Cleonimus, were found around a pulsar. I remember the day quite strongly. It was back in 1991. I think it was in November. I was working at Haystack Observatory as a high school student and working at my computer right beside the printer, smelling ozone all day. My research mentor came flying in, closed the door, and said, "Oh my God, I've got to tell you." And he told me about these new little worlds that aren't real planets. They're more like fragments of debris, but they're in orbit around pulsars. And this was the first time we ever had confirmation of a solid object that wasn't a star out there orbiting something that once was a star. So Hanny is, let's see, I don't mean to be magnetic field shaming. So let's see. Hanny is asking, for what distance would a pulsar be dangerous? I don't know off the top of my head. I'm sorry. And it would definitely depend on where you were in relation to the pulse. Okay. Other questions? Yeah, please go ahead and tag me. It will really help me find your questions. So while you're getting your questions into the chat, let me tell you a little bit more about what you can expect here at CosmoQuest X. We are a science channel that this is part of our day job. We are here bringing you science, bringing you the software needed to do the science, and communicating out live events as they happen. We have an entire team of us that you'll see off and on around this stream, but I will be, in general, your primary host. On Monday through Friday, most Mondays through Fridays, we bring you at 1 p.m. Eastern, 6 p.m. Universal Time. That is 10 a.m. Pacific, the daily space. This is your daily dose of all that is new in astronomy and space science. And we also cover launches, live news events. We're bringing you the press coverage from the American Astronomical Society meeting. Thank you for the follow. And everything we do is aimed at getting you more information to better know what is being discovered about our universe. This week, the daily space will be 1 hour late. This is because I can't be in two places at once, and Annie normally does cover that for me on Thursdays. This week, Annie is out at the American Astronomical Society meeting, and she's going to be bringing us updates every day at 5 p.m. Eastern, 2 p.m. Pacific. That's 10 p.m. Universal Time. This will be followed by the afternoon press conference from the AAS meeting. Thank you so much for the bits. Thank you. So I see a question. Is TESS releasing data soon? What can be discovered so far? Your English is just fine. Don't worry about your English. And thank you for the bits, Coupon. Thank you so very much. So TESS, they had a data release fairly recently. Thank you for the follow. And TESS is in an awkward position. The mission was really designed to be launched hand in hand with the James Webb Space Telescope, which did not launch. And so what TESS is doing is it's systematically going through and observing, I believe it's 13 different fields on the sky over and over and over. They recently did a data release of the first few fields. And in each of these fields, they're looking at the nearest stars and systematically observing a volume of space near the planet Earth for planets going around those nearby stars. Now, the reason that they're looking at nearby systems is so that we can do follow-up of these stars that have been found to have transits going on while the transits are going on, and use that information to point high-resolution spectrographs at the planets and study their compositions. Now, unfortunately, no James Webb. They're doing what they can using the very large telescope system of 4 telescopes down at Paranal in Chile. It's not quite the same thing, but they're doing what they can. They are finding planets. They are reporting that their spacecraft is working well, and we're just going to have to see what comes of it. Thank you so much for the follow, Lokestar TV, and all the rest of you who have followed and everything else today. So what other questions can I help you answer? As a reminder, we're a production of the Planetary Science Institute working in collaboration with Youngstown State University. This is actually part of our day jobs, and we have our day jobs thanks to donations from people like you that really made the difference when we lost our funding. So thank you for allowing us to be here. So Life Taken Biatch is asking, how much does it usually cost to build a telescope that can see transits, etc.? So to see a planetary transit, what you really need is a highly accurate system, not a large system. This means that you can actually see transits 1 star at a time using a 4-inch telescope in your driveway. So it's possible that for a few $1,000s, really you want to spend at least $30,000 to get a highly accurate system, so you need good quality optics on your telescope. You need an extremely accurate drive that your telescope is mounted to that will keep your telescope pointed at the star. And you need a high quality camera on the back end. For about $30,000, you can get a small, good enough system to observe transits from your driveway, if the sky is really good in your driveway. Now, to be able to do a survey that is detecting transit after transit after transit, such as we've seen with the Kepler mission and we're now seeing with the TESS and Gaia missions, you need to have a large field of view, a highly accurate system, which means you want to get up above the atmosphere to be able to do it for your entire field of view. Here on the Earth, across our field of view, you're going to have all sorts of variations due to twinkling, due to atmosphere, due to all sorts of stuff. But once you start talking about putting a telescope in orbit, now you're starting to talk at, instead of $30,000, you're looking at an absolute minimum of $30 million to launch a CanSat. And the costs just go up from there. I don't know what the final cost was for the Kepler mission or the TESS mission, but those should be just a Google away. And it's not cheap. It's not cheap. So let's see. Yes, they used completely basic telescopes for the occultations they used to determine the shape of ultimate Thule. I'll explain that in just a minute. I just want to see if there's any questions up above that I've missed. Okay, so I will come back to the questions above that that I missed in just a second. So you may have recently heard that there were, and I'm going to do this with turtles because it's turtles all the way down. There were observations made from the surface of the Earth that allowed them to determine that the ultimate Thule system was roughly shaped like one turtle sitting on the head of another. Now, the reason that they were able to do this is they observed stars passing behind from a variety of different pathways the object. And what they did was they timed when was it that their stars, in this case the point from my pen, I need to get a little tiny flashlight, when the star became invisible from each of the different observers, that timing told them, well, this is when Ultimate Thule 2014 MU69 is blocking out the light from that star. By measuring from a variety of different places on the surface of the Earth, doing all the trigonometry, and this is trigonometry, it's not calculus. By doing all the trigonometry, they were able to figure out the shape of the object on the outskirts of our solar system. So yes, that's how they did it with completely regular, everyday, off-the-shelf telescopes. So Giexvolved is asking, what is your favorite exoplanetary system? Do you have a fave? Okay, so I have to admit, because of its educational potential, I personally like the system Tau Butis B. Its abbreviation is Tau Bu B, and it lets me explain exactly how we get at the names of these systems. Tau means it is the 10th star in brightness in the system, where alpha is the brightest, then beta, gamma, so on through the Greek alphabet until you get to the letter tau. Once you get to the 10th brightest star in the Buddhist constellation, which we abbreviate as Bu because we're too lazy to write out the word Buddhist. B means it is the first planet in the system. Now, it turns out this is actually a binary system, so this object's full name would actually be Tau Bu B B. So it's Tau Bu B B. I just love how stupid it is. It's 12-year-old bathroom humor. Forgive me, it happens. Beyond that, I don't know. I also have an affinity for Kelt 9b. This is a planet that is being blasted apart by the hot star it orbits. And the reason I like it is because everything I was ever taught when I was in school said hot stars would never have planets. And this planet is out there saying, you were wrong. I'm only here for a short period of time. But while I'm here, I'm where I shouldn't be. I like things that do the things they're not supposed to do. Okay, so Hanny is asking, could a rogue Jupiter freeze solid? I'm not sure if solid's the right word, but the atoms sure would slow down. So yes, you'd end up with a very cold, whatever happens when hydrogen is at that large a density. I don't know if you call that ice. I just don't. But you definitely end up with a much more solid object. So thank you so much for the follow. So stupid Twitch chat is asking, is the dark side of the moon a good place to put a telescope? Do the Chinese have plans to put a telescope on the dark side of the moon? So thank you, Lives for Trauma, for the follow. So saying it's the dark side of the moon is one of those things that we do that really, really mucks with people's brains. The dark side of the moon is just the side of the moon we don't see. It's dark intellectually, but it's no more bright or dark than the side of the moon that we always get to see. What's happening, to return to my turtle example, because I live in a world of turtles. So here is our lunar turtle. And so we're going to pretend that this is the moon and this is the earth. I know that these are not the correct shapes, but hey, at least they're not flat. So as the turtle goes around and around the cup, it always keeps the same side facing the planet Earth. So it's going around and around and around. It's actually doing it on an elliptical orbit. So as far as the teacup is concerned, the turtle simply has a beautiful shell. Now the thing is, if you guys at the camera are the sun, right now you're getting to see the shell, and right now you're getting to see the belly. The sun is in the same position. It sometimes gets to see the face of the moon, and it sometimes gets to see the far side of the moon. This means you have the same number of hours of daylight, or in this case, the same number of days of sunlight on the moon for every square piece of space along the equator, no matter where they are, near side or far side. So yeah, everywhere on the moon is a perfectly fine place to put a telescope, but in the radio, not the optical. It turns out that if you put on the far side of the moon, the far side of our turtle, a radio telescope, the moon will block out the radio light that we're generating here on Earth. It does absolutely nothing for you in the optical and the infrared. Yeah, sun is still out there to curse you. But it does a great job for blocking out the Earth's radio light. So the Chinese aren't currently planning to build a telescope that we know about, but that's what we know. So let me see, scrolling down. Yeah, we do need to bring the costs down. Yes, you can totally ask me questions over on the CosmoQuest Discord. Please just at me so I can find them. So I don't know if the snowman outline is always facing us, Hanny's Vorverp. One of the cool things that's going on is we have our I'm now looking for something much smaller that I can use on my desk. Wow, I have a lot of turtles around here. Okay, I don't know where Marvin the Martian went, but I also have a Tasmanian devil. So we're going to make the Tasmanian devil our New Horizons spacecraft. As New Horizons flies out, in the perspective of New Horizons, we are constantly maintaining the same orientation. But while the same orientation is maintained relative to the motion of the spacecraft, I haven't figured out yet how different things will look over time from the perspective of the planet Earth. It's all a matter of where you're looking from. So as far as New Horizons can tell, 2014 MU69 is rotating in the plane of the sky. I don't know how it looks from the planet Earth. Thank you for finding that link, Paranor. Okay. Diablo BG is saying, if we were going to colonize the solar system, what is the most plausible way to do it? You know, I don't know how to answer that anymore. I think the best route to go is to find ourselves a nice asteroid, hollow it out, spin it up, and live on the inside, kind of like in the Expanse TV series. But we don't know yet just what is the density. Is a standard asteroid going to totally fall apart? We need to learn more. More data needed. I think that's the best answer. It's true, Hanny, with the moon, you can put things in the craters at the pole and they'll never see light. But the other side of that is you can put things up on the crater rim and they'll only ever see sunlight. So there are both constantly lit and constantly dark points at the poles. So Love Star TV is asking how much mass would be required to produce an artificial sun. Roughly 80 times the mass of Jupiter. We don't have it hanging around, so that's not going to happen. My stormtroopers disappeared last time I cleaned in here. I need to figure out where they went to. So let's see. The ecliptic is not aligned with the plane of the galaxy. It's not. No, it's so, yeah, it's, I know, I have an upset puppy now. I am going to have to go soon because of, let me show you. Come here, little one. Come here. Come here. I know. You're rolling on your belly and that makes you, ooh, I got you. This is Stella. This is Stella Sky. She is part evil, but mostly Australian Shepherd and cute. And she has been dead asleep throughout the entirety of this stream. And she just woke up and she is yawning and licking my face. And this usually means she needs to go out. So I will return tomorrow. Here, let me get your face on camera. I will return tomorrow. She's having nothing to do with this. And I will bring you more news from astronomy and space science starting at 1 p.m. Eastern. That is 6 p.m. UT, 10 a.m. Pacific, when we will be bringing you the daily space. So please give us a follow. Find out when we go live. Follows are free. As always, we are sustained by your subscriptions and every bit really matters. We have set up a Patreon and we have all sorts of cool benefits for those who follow us over on patreon.com/CosmoQuestX. I thank all of you so much for being here today. We do this for you. Our goal is simple, to get you learning and doing science. And I hope you learned at least a few things today. So thank you, and wherever in the world you may be, have a fabulous morning, evening, or afternoon. And remember to go outside and look up. Bye-bye. And I will be rating someone.